Hello, honors chemistry students. Hope you are staying safe and warm on this snow day. So what we're going to be doing is starting our next unit on chemical reactions, which is chapter 9. Today we're going to be taking notes over writing out and balancing a chemical reaction, and then also how to identify different types of chemical reactions based on their specific reactants and products. And then you will have a corresponding worksheet to complete, which is balancing and reaction types, that you can find in the homework folder of this unit. And you're not sure what's going to happen with tomorrow, whether we'll be in person or e-learning, but you're welcome to print it out, and if we are in person, turn it on paper, or you can do it right on Notability and then upload it to the next class period's Schoology assignment page for the day that it's due. So it'll be due our next class time, whether it's in person or e-learning. It'll be due next class time, which will either be Friday or next Monday for some of you. So here we go with our notes. So again, this is chapter 9 on chemical reactions, and we're first going to look at just kind of repeat what we talked about way back when in the beginning of the school year about indicators of a chemical change. But anytime we are forming some new substance, that is technically a chemical reaction. And as you've seen with some of our labs, and again what we talked about in the beginning of the year, there are a few different things that can indicate a chemical change. One of those is if we have a color change, and unfortunately if we are in person, I have some demos for you, but I'll show you those next time as we go through this chapter, when we talk about other specific reactions. So you'll still get to see the demos that we do. We could form a solid, which is known as a precipitate, kind of like the snow that's coming down is a solid form of precipitation. Oftentimes we use a down arrow. When we get to that part of the chapter, we'll talk more about that. It could also form a gas. In that case, you would see bubbles going on, and we would use an up arrow to indicate that we're making a gas. And then it could get hot or cold as the reaction either absorbs or releases heat. So those are some indicators of a chemical change. And sometimes there is nothing, sometimes it just looks the same as it did before, but it formed new substances. But if it does one of these things, we definitely have a chemical change going on. So the way we set up and write a chemical reaction, we have to follow a few criteria. We always put the reactants, which are our starting materials, on the left side of the equation. And the products are ending materials. Those go on the right side of the equation. And we have an arrow, which is known as a yield sign. You can see that over here on this little chart here. That's known as a yield because it's showing that we are taking reactants and forming or yielding products. So that's the one big difference between a chemical reaction and a mathematical equation, is we use an arrow as opposed to an equal sign. And there are other types of arrows. There's a double arrow. We really won't use that in honors chemistry. We'll talk more about that in AP. And then we can put things on the arrows too, which those are catalysts, and we'll talk more about that as that comes about later on in the chapter. So as we've said before with the other things we've done so far in this class, we always have to obey the law of conservation of matter. So when we're writing out a chemical reaction, we have to make sure that all of the elements are equivalent. There are equal amounts of elements on both sides of the arrow. So however many reactants we have to have the same amount of those elements on the product side. All they've done is rearrange themselves. So we always have to have the same amount of matter on both sides of the arrow. Now sometimes you will see the different states of matter like we have here, solid, liquid, or gas, or AQ, that stands for aqueous, and we'll talk more about that later on in the chapter. So sometimes you'll see those included. Other times you don't have to worry about including those. So just, if the problem says include states of matter, then put whether it's a solid, liquid, or gas, or aqueous. But most of the time it really won't. The up and down arrows, we will use those a lot as we go through this chapter. Okay, so next we're going to look at how do we balance these chemical equations so that we are obeying the law of conservation of matter, because again, we do not have the power to create or destroy matter, so we have to make sure we have equal amounts of it on either side of the arrow. Now, I know you've talked about this before in biology and even in middle school science, and those science teachers may have given you different ways to balance the equations, and that's fine. There's lots of different ways you can go about balancing these equations. I'm going to show you kind of the order that I go in that I think makes it as easy as possible. So you're welcome. I recommend following that order, but as long as it ends up balanced on both sides at the end, that's all that matters. Okay, so and some reactions are very complicated to balance, and it may take you a couple tries to do it. Others are already balanced as you write out the reactants and products, and you don't even need to do anything. But I highly recommend following these steps. So we'll go through some steps, and then we'll do some examples and show you how these steps help you get it balanced. So one thing in terms of balancing, the only thing we can do to balance the reaction or equation is add whole number coefficients in front of the compounds. We cannot change the little subscripts in the formulas, like when we're crisscrossing charges, or the little numbers with the prefixes for molecular compounds and organic compounds. We can't change those because then that changes the substance. So the only thing we can do to balance the chemical reaction is to put whole numbers in front of the compounds. So I like to balance all the metals first. Sometimes you may only have one metal, sometimes you may have two or three, but go through and balance all the metals first. Then, if you have polyatomic ions that stay together as a whole unit, balance those as a group, like phosphate or nitrate. If you have those on both sides of the arrow, balance those as a whole unit. Now, we will see some examples that the polyatomics break apart, and in that case, when they break apart and are no longer the same polyatomic on the product side, then you would balance the elements individually. But if it stays together as a polyatomic from the reactants to the product side, you can balance it all as one unit. Then after you've done both of those things, balance any nonmetals with saving hydrogens and oxygens for last. So balance metals, then polyatomics, then any nonmetals, and then the very last two things will be balancing the hydrogens and oxygens. And that's usually because there's so many hydrogens and oxygens, and they're often in multiple places in the chemical reaction. It's just easier that you save those for last. And sometimes they'll already be balanced by the time you get to them. So that's the order I recommend balancing a chemical equation in. A few other tips. If you're stuck on an odd number of atoms of something, try doubling it. For whatever reason, even numbers are just much easier to balance than odd numbers. That's not to say you can't have an odd number of something, but if you can't get something to balance and it's an odd amount, try doubling it and see if that makes it better. As you go through those first three steps of metals, polyatomics, and then nonmetals, if as you're doing those, as you're balancing other elements, that changes something you already balanced, go back and rebalance it before you continue on. So make sure you fix any elements that change along the way and rebalance them before you keep going on to the next step. And then once you think you have the entire reaction balanced, If all the coefficients can be reduced, reduce them. We want them always reduced down to their lowest whole number ratio. Now, if there's a 1 in front of any element, which you don't have to write the 1s, you can if you want to, but you only have to write 2s or more. But if there's a 1 in front of any substance, then that's already its lowest whole number ratio. But say you have 2, 2, 4, 4, something like that, you can divide all those by 2 to reduce it down to its lowest coefficients. Okay, so we're going to do some examples and see how we can apply these rules to make balancing reactions as easy as possible. Okay, so here's our first reaction. We have sodium sulfate reacting with aluminum hydroxide to form sodium hydroxide and aluminum sulfate. Now, one thing that you might find, again, I've said this hundreds and hundreds of times, if you find yourself not being able to balance a chemical reaction, you probably want to look at your formulas to make sure you've got them written right. Because if you've written a formula wrong, it can be pretty impossible to get it balanced or get it balanced correctly. So that would be the number one thing. If you're struggling to get the reaction balanced, make sure you have all your formulas written correctly. So here's what we call the skeleton equation, just writing out the reactants and products before it's balanced. So that sodium sulfate's Na2SO4 reacting with aluminum hydroxide, so AlOH3. So those are our two reactants right there. And again, I've got my formulas written out correctly. And then our products, sodium hydroxide and aluminum sulfate. And again, I always want to make sure my formulas are correct. Otherwise, it's going to be pretty tricky to balance. Okay, so this is, again, our skeleton equation. We want to get this all balanced so that we're not creating or destroying matter. So our first rule is to balance our metals first. So let me get my pen. Let's see how this works. Where did my pen go? Oh, there it is. Okay, so now we have two metals. We have sodium and we have aluminum. You can do whichever one you want first. I'll just do sodium first since it's written here as our first reactant. So this little 2 here from our crisscrossing, that tells us on this side of the yield we have 2 sodiums, but over here we only have 1. So I'm going to put a 2 there to balance it. And so now my sodiums are balanced on both sides. And then I'm going to do the same thing for aluminum, my other metal. I've got 1 aluminum on the reactant side, 2 aluminums over here. So to balance those, I'm going to put a 2 in front of this aluminum. So now my metals are balanced. That's all my metals I have. Can go on to the next step. And the next step is to balance polyatomics that stay together. Now for this, oh, I've lost my pen again. Where'd it go? It's so hard to see. Where'd my pen go? There we go. Okay, so we have sulfate and we have hydroxide. And again, they both stay together. We have a hydroxide and sulfate over here, so we can balance those as whole units. Again, it doesn't matter which one you want to balance first. I'll just balance sulfate first since we have it written first. So over here on the reactant side, I have 1 sulfate. Over here on the products, this little 3 tells us we have 3 sulfates. So I'm going to put a 3 in front here. Now, before I move on and balance the other polyatomic hydroxides, if you'll notice, I've just changed how many sodiums. I'd already balanced the sodiums earlier, but now balancing the sulfates, I've changed the number of sodiums. So now that I've done that, I need to go back and fix my sodiums. So let me erase this. And I'm going to put a 6 out here in front. Oops, sorry, that's supposed to be a 6. So now my sodiums are back to being balanced. So again, that's one of the rules. If you've changed something you've already balanced, rebalance it before moving on. And now we want to check our other polyatomic, lost my pen again, there it is, which is the hydroxide. And, oh, didn't mean to do that, sorry. Okay. So I have 2 times 3, so I have 6 hydroxides on my reactant side, and now after rebalancing the sodiums, I have 6 hydroxides on the product side, so this reaction is now balanced. And this is as low as it can go, and again, you don't have to write ones for coefficients, but because there is only one aluminum sulfate, I know that this is reduced down as low as it possibly can go. Okay, so again, you don't have to write the 1 if you don't want to, so I can erase that. But you can, especially if you just want to make sure that you've checked everything. You're welcome to write 1s in there. It kind of helps you keep track of things. Okay, so hopefully those rules made more sense. So if you're wondering what that noise is, that's my dog. Well, one of them, Ozzy, he's snoring right here. He's my helper. I've bored him to sleep. Okay, so our next one is aluminum metal reacts with oxygen gas to form aluminum oxide. So if we write that out, our reactants, aluminum is just plain old Al. Oxygen, remember, is one of the diatomics, so that's O2. Those are our reactants. And then to form, that tells us that that's our yield sign when you see the word to form. And then aluminum oxide, that is our product, which again, we have to crisscross our charges. Gotta make sure you have your formulas written out correctly. So let's try balancing this. Again, we want to balance our metals first, which in this case, all we have is aluminum. Just lost my, there we go. So we've got 2 aluminums. Oops, that's supposed to be a 2. 2 aluminums on our product side, so I put a 2 out front here for 2 aluminums on the reactant side. And then we don't have any polyatomics, we don't have any more metals. The only thing left is oxygen. On the reactant side, we have 2. On our product side, we have 3. So this is one of those where, you know, it's kind of an example of we have an odd amount, so let's make it even. Or you could look at it, the least common multiple between 2 and 3 is 6. So I'm going to put a 2 out here to give us 6 oxygens. Now remember, we already balanced our aluminums and we just changed it. So before I continue on and forget to fix the aluminums, I'm going to go and balance those. And now we have 4 aluminums. I don't know why that does that. Yikes, that's supposed to be a 4. There we go, 4 aluminums. And now we can finish up with the oxygens, which we have 6 oxygens, so I'll put a 3 out here. And again, that is our lowest whole number ratio of a 4, a 3, and a 2, so we can't reduce that anymore. Okay. All right, next reaction, we have phosphoric acid reacts with magnesium hydroxide. Those are our reactants. And then we have the to form magnesium phosphate and water. So when we write out our skeleton equation, it looks like that. Again, want to make sure you've got all your formulas written correctly, correct crisscrossing and all that good stuff. The reactants on the left side of the arrow, the products on the right side. So again, we start with our metals. Our only metal in this reaction this time is the magnesium. So over here on our reactant side, we just have 1. Our product side, we have 3. So I'm going to put a 3 out here in front. And now our magnesiums are balanced. Now we also have two polyatomics. We have phosphate and hydroxide on our reactant side, but on our product side we only have phosphate. So we can balance the phosphate as a whole unit, which we have 2 on the product side but only 1 on the reactant side. So I'm going to put a 2 out front to balance phosphates. But the hydroxides don't stay together. Over here there's no hydroxide, we've got water. So that's an example where, and hydroxide will do this a lot, it separates and we can't balance it as a whole unit. We're going to have to balance the hydrogens and the oxygens individually. So we're done balancing our polyatomics, which brings us to balancing our nonmetals, and our only nonmetals left to balance are the hydroxide and the hydrogen and oxygen from the hydroxide. Now, we've already balanced the oxygens in the phosphates, okay? Those got balanced when we balanced the phosphates, so we're not counting those. We're just counting these oxygens here and here, and the hydrogens here and here. So again, the rule says leave the hydrogens and oxygens for last, so it's best to do hydrogens first, then oxygen. So if we count up our hydrogens, we've got 6 right here, and you're welcome to, sometimes I'll put little sums here to help me keep track, especially when they're in more than one place. So I have 6 hydrogens here, and then I have 3 times 2, I have 6 more hydrogens here. So I have a total of 12 hydrogens on my reactant side. Okay, so to make 12 hydrogens, darn it, I need a 6 right there. And let me clean that up. Don't know why. There we go. Let's see if I can write that better. Nope. Okay, well, that's a 6. That's supposed to be a 6. So we have 6, putting a 6 here gives us 12 hydrogens here, so now we match. We have 12 and 12 hydrogens. And then let's check our oxygens. Again, we already balanced the oxygens and phosphate, so we just need to count these oxygens here, which is 6, and in this case the oxygens already balance. And again, let me clean up all of this. So, and well, they're both pretty bad. Okay, so our overall balanced reaction is 2 phosphoric acids reacting with 3 magnesium hydroxides to form magnesium phosphate and 6 waters. So that is our balanced chemical reaction. All right, then this last example, we have butane, which is C4H10, reacting with oxygen to form carbon dioxide and water. So again, here's our skeleton equation of our reactants, the butane and oxygen, and then our products, carbon dioxide and water. Now we don't have any metals to balance. We don't even have any polyatomics. All we have are nonmetals. And remember, it says to save the oxygens and hydrogens for last. So that means I'm going to balance my carbons first. So I have 4 carbons here. So let me put a 4 here. And again, saving oxygens for very last, I'm going to balance the hydrogens next. So we have 10 hydrogens over here with the butane. So let me put a 5 here to make 10 hydrogens on the product side. And now we can balance our oxygens. So we have 8 here, because 4 times 2. Did that again. And then we have 5 here with the water. So that gives us a total of 13 oxygens. Now, because oxygen is diatomic right here, we can't put a whole number here, okay? And we need 13. So this is where that rule of try doubling an odd amount comes in handy. So we can't balance 13 oxygens with O2. So let's double the number that's making us have an odd number of oxygens, which is this 5 right here. So let me erase that. I'm going to erase all this other junk too. So I'm going to erase that, and I'm going to double it. So I'm going to make that 10. Now before we go on and balance the oxygens, we just changed the hydrogens. We now have 20 hydrogens. So now I've got to rebalance those, because remember, you want to fix anything you've already balanced. So I need a 2 out in front here to give us 20 hydrogens on the reactant side, which changes our carbons. Now we have 8 carbons, so I need to rebalance the carbons on the product side so that they're balanced again. That's an 8. Okay, so now that we've fixed and rebalanced everything that got changed, let's count up our oxygens. So now we have 16 here with the carbon dioxide and 10 here with the water, so that gives us a total of 26. 26. And we can make 26 oxygens over here with the O2 by putting a 13. And then clean that up. Okay, so that's how we balance those, and that's what we mean by doubling. Again, that's not to say that you can't have odd amounts, but if you can't balance something because there's an odd number, try doubling whatever's causing it to be odd. So again, there's multiple ways to go about balancing it. In the end, there's only one correct combination. However you get there is up to you, but I recommend doing the order we were just talking about. Okay, then our final topic today is in section 2 of chapter 9, looking at the 5 different types of reactions that we're going to be studying in detail throughout this chapter. Here today, I'm just going to give you the basics of how to recognize them, and then next week we're going to get into specific details about each of these different types of reactions, and ultimately we're going to be predicting the products. But for now, you just have to be able to identify what type of reaction it is based on the different compounds and what's happening with those compounds. So our first reaction is a combustion reaction. A combustion reaction is where we have a carbon compound that burns with oxygen. That's going to form carbon dioxide and water. It also releases a lot of heat, which is an exothermic reaction. So just your basic example of a combustion reaction is we have some type of carbon compound. It could be an alkane, like what we learned how to name last semester. In that case, you'll be expected to know the formula, but if it's some other carbon compound that's not an alkane, I will give you those formulas. You do not need to know other organic compounds besides the alkanes. And then oxygen, and then here are our products. It always makes carbon dioxide and water, and this is kind of what it looks like in the molecular format. Our methane, if you remember building the little molecules with oxygen, forming carbon dioxide and water. The next type of reaction is called a synthesis. It's also known as a combination reaction. I really don't use that term because it's so similar to combustion. It's easy to confuse, so I always call them synthesis reactions. And synthesis reactions are where we start with 2 or more reactants, and then they combine together to form one product. And that's your clue that it's a synthesis reaction, is that it just has one product. So a synthesis reaction will look something like this. We have reactant A and reactant B. They're going to combine together to form one single product, compound AB. And that's what's going on here. This is actually hydrogen, 2 hydrogen diatomics reacting with 1 oxygen, forming 2 waters. Okay, so that's an example of a synthesis. But again, we have one product, the water here. How many of them we have, that depends on our balancing, but we just have one substance for our product. The third type of reaction is called a decomposition reaction. This one you might have talked about in biology. It's actually the opposite of synthesis. With decomposition, we start with one reactant, and then usually it requires or uses some type of heat or energy to form multiple products. So that's your clue. We have just one reactant, but end up with multiple products. So if we just switch the synthesis reaction around to AB being our only reactant, and then it's separating into substance A and substance B, two different substances, that's a decomposition. So again, we can just flip this reaction around here where we made water with synthesis. Here we can separate water into hydrogen and oxygen through decomposition, but that does require some energy. And again, when we talk about these different reactions in more detail starting next week, we'll get into all of that other stuff as well. Right now you just need to spot it based on the clues that it's one reactant making multiple products. The next type of reaction is called a single replacement. It can also be referred to as single displacement reaction, but I think this book uses replacement. Oops, what happened here? There we go. So in the single replacement reaction, that is where we have a single element replaces an element in a compound to form a new element and a new compound. They're really snoring away. This is really boring them. So here is your basic single replacement setup. So we have element A, whatever that may be, is going to react with compound BC. And so what happens is element A comes in and replaces element B in the compound, or C, it depends. It could replace either one. So then we have new compound AC and element B all by itself, which is what this picture is showing here with copper 2 chloride. That would be the compound reacting with single element zinc, and what happens is the zinc comes in and replaces the copper to form the new compound zinc chloride, and the element copper is all by itself now. So that's what we call single replacement, where we are replacing a single element in a compound to form a new single element, new compound. And then finally, double replacement, also known as double displacement, is another name for it. That's where we have two compounds as reactants, and they simply trade their cations, their positive ions, to form two new compounds. And you've got to remember to crisscross all of your charges where necessary. So here we have, as an example, compound AB, and it's going to react with compound CD. So what happens is A and C, those are the cations, because remember we always write the cations first in the compound. So A and C are our cations. They're just going to switch places. So now we have our products, compound AD and compound CB. So we have to re-crisscross charges if necessary, and then obviously balance after that. But we're just switching the positive ions. So that's what this picture is showing over here. And we'll actually do this reaction when we come back to school. I'll show you this as an example. So we have the compound silver nitrate reacting with sodium chloride. So silver and sodium are positive ions. They're both metals. They both happen to be +1 metals. They're just going to trade places. So now the silver is going to combine with the chloride to make silver chloride, and the sodium is going to combine with the nitrate to form sodium nitrate. So that's double replacement. So hope you took good notes, and again, you're going to, for the next class, whether we're in person or on e-learning, going to complete the balancing and reaction types worksheet, and you can either print it off and turn it on paper if we're in person, or if we're e-learning, you will need to upload it to the next class day's Schoology page as a PDF. So if you have any questions or need any help, just send me an email, and I'll get back to you as soon as I can. Have a good day. Stay safe and warm. Bye.